Hello, my name is Ram Goel, and I'm going to be presenting my research today, which relates chip firing on infinite graphs to geometric block stacking schemes. So my research is in the field of chip firing, a mathematical way to model the flow of objects in a network. Specifically, my research relates a property of chip firings known as the firing lattice to structures involving geometric block stacking. And I use this connection to extend previously known results, as well as answer new questions. So my research basically takes the field of chip firing and connects it to a completely separate field of the role of geometric shapes and geometric structures, and I'm able to use that to solve problems in the field of chip firing. So before we can understand what a chip firing is, we have to understand what a graph is. A graph is a mathematical way to represent a network and connections between a set of objects. So specifically, a graph has a set of nodes known as vertices and a set of edges between certain pairs of vertices. The edges represent the connections between vertices. For example, um, we have four vertices in this graph called the diamond graph, and we can see the certain edges that are being displayed. So this is an example of a graph, and graphs are very versatile. This is the most abstract way to express them, um, but graphs are used in many various contexts, especially in mathematics and computer science, and are used to model various kinds of networks such as GPS satellites, transportation networks, social networks, and much more. So graphs are very versatile. But let's get into what a chip firing is. So a chip firing on a graph is a way to model the flow of objects in a network. So formally using graphs, on a graph, we start by placing some number of chips on each vertex. The number of chips is just a number associated with each vertex, and this number changes according to the following rule. If a vertex has at least as many chips as neighbors, a neighbor of a vertex is a vertex that it's connected to by an edge, then it can send one chip to each of its neighbors and lose that many chips. So we call this firing V if it's able to do this. And we can think of this sort of, before I get to an example, as a group of people, and edges represent friendship. And you have some amount of money, and you can send $1 to each of your friends, and you lose that amount of money. That would be called firing the vertex that you correspond to. So, for example, if we have go back to the diamond graph, um, we can start off with two vertices, two chips, six chips, seven chips, and four chips, and we can fire the four because it has more chips than neighbors. It has at least as many, and hence we can send one to each of its neighbors. We can also use the tools of linear algebra to attack chip firing problems, but this will not be necessary for the research I'm going to be presenting, but it's something important to keep in mind, specifically the Laplacian matrix and matrices and vectors. So why is chip firing relevant? Well, chip firing turns out to actually be one of the most practical and directly applicable branches of math. So at its roots, chip firing is a model for dispersion, flows, spreads in any sort of network. And this makes the theory surrounding chip firing very applicable at a practical level to all sorts of network problems. Specifically, chip firing has shown to accurately model, and theorems in chip firing have been shown to actually help improve things in traffic flow optimization, earthquake detection, the spread of uncontrolled wildfires throughout forests, and even infections of viruses over large groups of people. The last two are pretty relevant to us in Oregon, and well, the last due to COVID, which is worldwide, and the third because wildfires recently affected our state of Oregon. And the point is that research in chip firing can directly improve society and save lives. So it's very important. One more piece of background for my research. My research focuses on a specific property of chip firings on infinite trees, known as the firing lattice of the graph. So consider a graph. There are many possible ways that you can fire its vertices and get different sort of configurations of chips. So the firing lattice is a way to organize all these pieces of information. And in specific, the firing lattice stores this information because on each level of the poset, a poset is a partially ordered set, which is a well-studied object in mathematics. The levels represent how many times the graph has been fired. So, for example, the first level is just if you fire once, second level, one level deeper, and so on. So here's where the research, my research question comes in. It has been shown in the past for infinite path graphs, which is a specific kind of graph that if you fire, so let me zoom in on this, that any firing of the infinite path graphs into some number of vertices um, can actually be uniquely determined by the number by how you drop blocks into this sort of V wedge. Um, and this has been shown because this specific case of infinite path graphs relates to the well-studied concept in mathematics of integer partitions and Young diagrams. So what we have here is that for any chip firing state of this infinite path graph, there's actually a unique way to drop blocks into this V wedge. By dropping blocks, what I mean is we have these squares, which you can think about as dropping like into Tetris and into gravity, and they fall due to gravity. And there's actually a unique way for each configuration of chip firings. So my research extends this to beyond infinite path graphs to any sort of tree. And I thought this was really intriguing, which is why I decided to try and extend it. And what we do is we are able to create a different sort of geometric shape for any kind of tree. And this uh, turns out to be in bijection, a one-to-one correspondence with what we were trying to study. So again, the goal is to convert a problem in chip firing to a problem related to geometric structures, which is easier to analyze. So the first step to constructing this geometric structure, later I'll explain the theorem in which I prove it's in bijection, but to get the geometric structure, there are two basic steps. One is to construct the condensation diagram of the tree. So we start off with an infinite tree, to recap, and we want to create the geometric structure in which block, stacking blocks corresponds to firing the tree T. So the condensation diagram is the first step. And what you can think of the condensation diagram of is sort of imposing a grid structure on the vertices of the tree. And this sort of, for example, on the tree T over here, on the left, the condensation diagram appears on the right. So the condensation diagram is a mathematical way to get a grid structure on the vertices. The second step is the hinge diagram. This is the geometric structure in which we drop blocks. This is created by topologically gluing um, certain things called triangular pages. And it turns out that gluing these actually gives you the geometric shape into which we're going to drop blocks. The construction is a little complicated. So for example, you can see down here, we have these triangular pages and the colors represent how we are gluing them. And it turns out dropping blocks into this structure is in bijection, like I'm saying in this theorem. This theorem gives an explicit bijection, a one-to-one correspondence from any firing of chips on an infinite tree T to dropping blocks into this hinge diagram. And analyzing the dropping of blocks in the hinge diagram is much easier than analyzing the firing of chips on this massive tree. So in summary, what I've done is relate these two fields of chip firing on infinite trees to the geometric stacking of blocks in a simple, relatively simple geometric structure. This theorem extends previously known results in the field beyond infinite path graphs to any infinite tree. So this theorem is exciting in itself, but can we extend it to prove other problems that were previously unsolved purely about chip firing? It turns out the answer is yes. There's something called the rank generating function, which is a function of a poset, a partially ordered set. Um, and it's well-studied property of these posets. And it turns out that this geometric interpretation helps us give an exact formula for the rank generating function for firing lattices of trees. And the formula I was able to discover is here. This is another theorem I was able to prove. And what this does is uses the geometric interpretation crucially to get this formula. This is a previously unknown form for the rank generating function. So in summary, my research extends known theory in the field of chip firing and firing lattices. Specifically, the bijection proved connects the fields of chip firing and combinatorics to the world of geometry and geometric shapes. And this connection can open up new areas of study and prove unsolved problems such as the rank generating function, which I just mentioned. The rank generating function was actually just for a specific kind of infinite tree. So my goal is to extend this to beyond, my future research goals are to extend this to beyond just k-rays, which is the tree I was able to find the rank generating function for, to any infinite tree. And my work will be sent for publication soon, and I hope to benefit people around the world with this research. Thank you for listening to my talk, and I hope you enjoyed it.